Materially flexible couplings accommodate axial and parallel misalignments between the input and output shafts by elastic deformation of a flexible element within the coupling. Since there is no relative sliding motion taking place between the elements of the coupling, materially flexible couplings do not require lubrication. Materially flexible couplings fall into two broad categories: metallic materially flexible couplings and elastomeric materially flexible couplings. The most common types of metallic materially flexible couplings are beam couplings, bellows couplings, metal disc couplings, and diaphragm couplings. A beam coupling is made from hollow tubular or solid bar circular stock. By cutting a helical slot on it, the coupling is usually connected to the input and output shafts using set screws. Beam couplings have a helix angle that can range from 0 for a straight slot, to a value less than 90 degrees. As the number of helical turns that the slot makes increases, the flexibility of the coupling increases, and it is able to accommodate higher values of angular and axial misalignment, and axial movement. Based on the number of helical slots that are cut on the surface of the beam couplings can have 1 start slot, 2 start slots, or 3 start slots. The larger the number of starts, the greater the torsional stiffness of the coupling. Beam couplings have many advantages. These are as follows. They can accommodate large angular misalignments between the input and output shafts, up to 90 degrees for some models. They can also accommodate large values of parallel misalignment. Large amounts of axial motion can also be accommodated. Beam couplings have good vibrations and shock loading handling capabilities. Because of their all-metal construction, beam couplings can be used in high-temperature applications. Beam couplings can be run at high speeds that can reach 10,000 rpm for beam couplings manufactured from hollow stock, to 50,000 rpm for beam couplings manufactured from solid stock. The main disadvantage of beam couplings is that they can only handle small torque values. The bellows coupling is made from a small diameter tube that is wound to form a cylindrical closely packed spring-like shape. The coupling is usually connected to the input and output shafts using set screws. The main advantages of bellows couplings are as follows. Their ability to accommodate angular misalignments up to 30 degrees. Their ability to accommodate large parallel misalignments. And their high torsional stiffness. The main disadvantage of bellows couplings is that they can only handle small torque values. Now let's examine the components of the metal disc coupling. This coupling is made of 2 flanged hubs that connect to the input and output shafts, usually using keys. The hubs are connected by a flanged hollow shaft. 1 or more metallic discs connect each hub to one side of the flanged hollow shaft. The discs are connected using screws to the hubs and flanged hollow shaft. On both coupling sides, the screws connect the metal discs in an alternating manner to the hub and to the flanged hollow shaft. The flexibility of the stack of thin metal discs allows them to deform slightly as the coupling transmits the torque load. For more coupling flexibility, at a reduced torque rating, less discs can be used in the disc stack. As more discs are added to the stack, the torque rating of the coupling increases, but the coupling also behaves more like a rigid coupling. Single disc pack metal disc couplings are not able to accommodate parallel misalignments. By using a double disc pack coupling, as shown here, parallel misalignment can be accommodated through angular flexing between the two end hubs and the central flanged shaft. Metal disc couplings have a number of advantages, which are as follows. They have a very long service life which is virtually unlimited if the coupling is used within its specifications. They can be run at high shaft speeds. They can also handle large torque values. Metal disc couplings also have some disadvantages. They cannot handle axial shaft motions. Furthermore, they can only handle small angular misalignments of about 1 degree. The design of the metal diaphragm coupling is similar to that of the metal disc coupling. The metal diaphragm coupling is made of two flanged hubs that connect to the input and output shafts, usually using keys. The hubs are connected by a flanged hollow shaft. A metallic diaphragm connects each hub to one side of the flanged hollow shaft. The diaphragms are connected using screws to the hubs and flanged hollow shaft. On both coupling sides, the screws connect the outer part of the metal diaphragms to the hub, and the central part of the metal diaphragm to the flanged hollow shaft. The flexibility of the thin metal diaphragms allows them to deform slightly as the coupling transmits the torque load. Although single diaphragm couplings are not able to accommodate parallel misalignments, by using a set of two diaphragm couplings, parallel misalignment can be accommodated through angular flexing between the two end hubs and the central flanged shaft. The flexing of the diaphragm also allows a small amount of axial shaft motion. Diaphragm couplings can be categorized in terms of the number of diaphragms used, into the single diaphragm type, and the multiple diaphragm stack type. As the number of diaphragms or their thickness increases, the torque rating of the coupling increases, but its misalignment handling capability decreases. In terms of the profiles of the diaphragms, they can be divided into flat diaphragm couplings, like the one shown here, that have a flat profile, and accommodate angular misalignment by stretching, and convoluted diaphragm couplings that have a wavy profile, and accommodate angular misalignment by unfolding their wavy profile. In terms of the shape of the diaphragms, they can be divided into solid diaphragms that tend to induce more bending stresses on the input and output shafts under a given angular misalignment while having a higher torque rating, and diaphragms with various shapes cut out of them that induce less bending stresses on the input and output shafts under a given angular misalignment while having a lower torque rating. Metal diaphragm couplings have a number of advantages, which are as follows. They have a very long service life which is virtually unlimited if the coupling is used within its specifications. They can be run at high shaft speeds. They can also handle large torque values. Finally, diaphragm couplings can handle small axial shaft motions. The main disadvantage of metal diaphragm couplings is that they can only handle small angular deflection values of about 1 degree. Elastomeric materially flexible couplings use a flexible elastomer element to provide the required elastic deformation within the coupling that compensates for misalignments of the input and output shafts, and cushions the transfer of power from the driver to the driven load. Depending on the way the load is transferred through the elastomer element, elastomeric materially flexible couplings can be divided into compression type couplings and shear type couplings. since elastomeric materials are usually stronger in compression than they are in shear. Compression-type elastomeric couplings tend to have higher torque ratings than their shear-type counterparts. The compression-type couplings are also usually able to accommodate higher short-duration overload torques than their shear-type counterparts. In general, compression-type couplings can withstand short-duration torque overloads of about 6 times their nominal torque rating. Shear-type couplings on the other hand are only able to withstand short-duration torque overloads of about 2 times their nominal torque rating. The shear-type elastomeric flexible couplings are able to accommodate higher values of angular and parallel misalignments than their compression-type counterparts without generating high bending stresses in the input and output shafts. The 3 main types of compression-type elastomer couplings are jaw couplings, pin and bushing couplings, and donut couplings. A jaw coupling is constructed of 2 metal hubs that are attached to the input and output shafts. The hubs have 2 to 7 jaws that protrude from their mating surfaces. A flexible elastomer insert, called a spider, fits between the jaws of the hubs. The flexible spider cushions the contact between the jaws of the hubs, compensates for parallel and angular misalignment between the hubs, and can absorb vibrations from the driver or the driven load. In addition to the general advantages of elastomeric couplings that will be discussed subsequently, jaw couplings have some extra advantages. The first is that their design is considered fail-safe. This is due to the fact that even if the spider is broken away, the hubs can still transmit the load by metal-to-metal contact between the jaws of the 2 hubs, until the spider can be replaced. The second advantage is that since only the spider teeth that are forwards of the driver hub are under load, the life of the spider can be doubled by advancing the idle trailing teeth into a driven position. The spider component of the jaw coupling can be manufactured out of several materials. These include nitrile-butadiene rubber, or NBR, urethane, Hytrel, bronze, nylon, and Viatin. Although bronze is obviously not an elastomer, it is still included here for comparison and because it is used in some specialized applications that involve subjecting the coupling to salt water. All the aforementioned spider materials except bronze can accommodate parallel misalignments of about 0.015 inches. Bonds can only accommodate a parallel misalignment of 0.01 inches. Except for bronze and Hytrel, that can only accommodate an angular misalignment of half a degree. The other spider materials can accommodate an angular misalignment of 1 degree. The temperature rating of the coupling varies according to the material of the spider that is used, with bronze and Viatin having the highest temperature rating of 232 degrees Celsius, and urethane having the lowest temperature rating of 71 degrees Celsius. Except for bronze, which has a virtually unlimited shelf life. All the other aforementioned spider materials have a shelf life that varies from 20 years for Viatin to just 5 years for NBR and urethane. NBR and Viatin have the smallest torque rating as compared to the other spider materials, while bronze has the highest torque rating. NBR is the best spider material in terms of its vibrations and shock loading dampening capabilities. Both Hytrel and Viatin, on the other hand, have excellent chemical resistance properties. Finally, nylon has the best electrical insulation capabilities amongst all the aforementioned spider materials, while bronze is an electrical conductor. The pin and bushing coupling is a compression-type coupling. This coupling is made of 2 hubs that usually connect to the input and output shafts using keys. Each hub has a set of pins protruding from its side that is opposite the other hub. The pins from each hub are inserted into elastomeric bushings that are pressed into the opposing hub. The bushings usually have a metallic sleeve at the center where the pins fit tightly. Due to the flexibility of the material of the bushing, the coupling can accommodate angular misalignments of about 2 degrees. However, the pin and bushing coupling can accommodate only small amounts of parallel misalignment. The pin and bushing coupling has good capabilities when it comes to dampening torsional shock loads and vibrations. The donut coupling is another type of compression coupling. It is made of two metallic hubs that connect to the input and output shafts, usually using keys. The hubs are connected by an elastomeric donut-shaped element, with embedded metallic inserts that are connected alternatively to the driver and driven hubs. When the donut-shaped element is first connected to the metallic hubs, using a set of cap screws, all segments of the donut are under compression since the cap screws force the donut to a smaller diameter. Since the metallic insets run the entire width of the donut-shaped element, the load is transmitted from the driver hub to the driven hub, by compression of the segment of the donut, between an insert that is connected to the driver hub, and an insert that is connected to the driven hub. The donut coupling can accommodate an angular misalignment of up to 3 degrees, and has good parallel misalignment capabilities. The donut coupling also has good torsional shock and vibration damping characteristics. The two main types of shear-type elastomer couplings are sleeve couplings and tire couplings. The sleeve coupling is made up of two metallic hubs that connect to the input and output shafts, usually using keys. The hubs have serrated sockets on their sides that are opposite one another. A molded tubular elastomeric sleeve fits within the serrated sockets of the input and output hubs. The most common elastomeric sleeve is made of a single tubular piece. Adding one split along the length of the elastomeric sleeve makes it easier to peel the sleeve away when it needs to be replaced. Elastomeric elements that are made up of two completely separate halves, like the ones shown here, are easiest to install and remove, but require a metallic retaining ring to prevent the sleeve from being detached from the hubs under high centrifugal forces caused by high shaft speeds. This design can accommodate angular misalignments of up to 2 degrees, and parallel misalignments of up to 0.05 inches. The elastomeric sleeve coupling also has excellent torsional shock and vibrations damping characteristics. It can accommodate up to a 15 degrees torsional angle between driver and driven shafts. There are two types of tire couplings: the corded type and the bonded type. Both designs can accommodate axial shaft motion well. Furthermore, both designs have excellent torsional shock and vibrations damping capabilities. The corded tire coupling is another type of shear elastomer coupling. There are 4 main components of the corded tire coupling. The first component is the two metallic hubs. The hubs are connected to the input and output shafts using keys. A tire-shaped elastomeric element connects the two hubs together. Just like an automotive tire, the tire element is usually made from rubber or a similar material, and has layers of reinforcing cording that is made usually from nylon. 2 clamping end plates are used to hold the tire to the hubs. The clamping plates are secured to the hubs using cap screws. This design allows angular misalignments of up to 4 degrees, and parallel misalignments of up to a 1/4 inch. The bonded tire coupling is yet another type of shear elastomer coupling. This coupling is made of 2 metallic hubs with keyways machined in them to connect them to the input and output shafts via keys. The hubs are connected together using the bonded tire element. The tire element, which is usually made from polyurethane, Is bonded to a metallic shoe. The metallic shoe is connected to the hubs using cap screws. The bonded tire elastomeric coupling has good angular and parallel misalignment handling capabilities. Elastomer couplings have a number of advantages. They are able to handle moderate angular and parallel misalignment, and axial motion. They also have good vibrations isolation characteristics. Finally, elastomer couplings have a cheap price as compared to other coupling types of the same power rating. The disadvantages of elastomer couplings include the fact that they are generally limited to small and medium power ratings. Elastomer couplings also are usually not very resistant to harsh environments such as extreme cold or heat, corrosive chemicals and ultraviolet radiation. The elastomer element usually has a limited shelf life of 5 to 10 years. The spring coupling consists of two metallic hubs that are connected to the input and output shafts using keys or set screws. The hubs have outer teeth machined on their opposing ends. A spring element is woven alternatively into the slots that are formed by the space between the teeth on each hub. The spring element transmits the load and provides the coupling's flexibility by sliding in its slots and mechanically flexing under load. A lubricant is used to lubricate the sliding motion of the spring and prevent excessive wear and heat generation. A protective metallic cover is installed around the spring element to contain the lubricant, to prevent the spring legs from leaving their positions on the hub's teeth, and to prevent contaminants from being mixed with the lubrication fluid. The cover can be split axially like the one shown here, or it can be split in a radial direction. The spring grid coupling possesses many advantages. It handles parallel and angular misalignments very well, without subjecting the input and output shafts to high bending stresses. It is able to accommodate large axial motions without generating high forces on the input or output bearings, by means of the sliding of the spring element within its grooves. The spring grid coupling also has excellent torsional shock and vibrations damping capabilities. The spring grid coupling also has some disadvantages. Due to the mechanical sliding motion of the spring element within its slots on the two coupling hubs, the coupling requires periodic lubrication. Furthermore, the spring element is difficult to install and replace. Review questions. Drag and drop the correct coupling name under the corresponding coupling. Right answer. In case of an overload, which of the following components should fail first? Right answer. Drag and drop the correct component name under the corresponding sleeve coupling component. Right answer. Which of the following best defines torque rating of a coupling? Right answer. Drag and drop the correct name under the corresponding compression type elastomeric coupling. Right answer. Which of the following can a double universal joint, that is equipped with an expansion joint, accommodate? Right answer. In a universal joint, how does the maximum amplitude of fluctuation of the output shaft velocity change with increase in the angle of misalignment between the output shaft and input shaft? Right answer. A belt coupling requires the pulleys attached to the prime mover shaft and the pump shaft to be. Right answer. Drag and drop the correct number of slot starts under the corresponding beam coupling. Right answer.